Hi everyone, my name is Agai and I'll begin by explaining the concept and mathematical modeling of a coilover suspension system. What is a coilover? A coilover is a type of suspension system used in vehicles to improve ride quality, handling, and vehicle control. The term coilover stands for coil spring over shock absorber. This is the diagram of coilover component. It consists of two main components, which is spring. Typically a helical coil spring. It stores and releases energy, providing resistance to compression and extension to support the vehicle's weight and absorb bumps. Secondly, damper or shock absorber, a hydraulic or gas-filled component that resists motion by dissipating kinetic energy, reducing oscillations, and controlling the rebound of the spring. Let's move to the derivation of the second order ordinary differential equation. The spring external force of the coilover is given by F spring equals to negative Kx. The damping force always opposes the motion of a mass and is given by F damping equals to negative Cx dot. By Newton's second law, the resultant force of an object is equal to its mass times its acceleration. Expressing acceleration as the second derivative of displacement x, we will get the final equation mx double dot plus cx dot plus kx equals to 0. From the solution of the ODE, we can determine the characteristic equation and the roots. The type of roots of the ODE depends on the value of discriminant delta equals to c squared minus 4mk. For case 1, when delta is less than 0, it is under damping. For case 2, when delta is equals to 0, it is critical damping. For case 3, when delta is more than 0, it is over damping.
Hi, I'm Fawaz, and I'll explain how we simulate the coilover suspension system based on the ODE we derived earlier. First, we choose the values for mass m and spring constant k to be 1000 kg and 30,000 Newton per meter respectively. From these, we can calculate the critical damping coefficient C. Substituting the values into the formula, we get the critical C to be 1.095 times 10 to the power of 4 Newton second per meter. Then we choose the other values for C for different cases, which are underdamping and overdamping. All the chosen parameters are tabulated in this table. For underdamped oscillation, C is less than critical C. The roots of the characteristic equation will be complex numbers. We take the initial displacement of the coilover to be 0.2 meter and the initial velocity to be 0. The displacement function will be as shown. For critical damped oscillation, C is equal to critical C. The roots of the characteristic equation will be an equal number. By taking the same initial condition as previous, the displacement function will be as shown. For overdamped oscillation, C is greater than critical C. The roots of the characteristic equation will be distinct. Again, by taking the same initial condition as previous, the displacement function will be as shown. With these functions, we can then plot the graph of displacement versus time for each case.
Hello, my name is Ifa and I will present and interpret the result of our simulation. For the underdamped case, C equal to 0.555 times 10 power to 4 ns over m, the system oscillates but with gradually decreasing amplitude. This behavior is common in real suspensions where comfort and performance are balanced. In the critically damped case, with C equal to 1.095 times 10 power to 4 ns over m, the system returns to rest quickly without overshooting. This is ideal for the passenger vehicles that prioritize comfort. Lastly, in the overdamped case, C equal to 2.222 times 10 power to 4 ns over m, the system returns to equilibrium without oscillating, but it does so very slowly. This might make the ride feel sluggish. For the comparison of the graph, we can see each case shows how damping impacts vibration behavior in a suspension system. Like the green one is for overdamped case, the blue one is for critically damped case, and the white one is for underdamped case.
Hi, my name is Nur Amira Adibah binti Ashrul. I'll now conclude our presentation by discussing the significance of our result. Let me explain why damping is absolutely crucial in vehicle suspension. First, damping controls oscillation. It is what prevents your car from bouncing excessively after hitting a bump. Imagine driving without any damping at all. The car would keep oscillating up and down indefinitely after every bump. Second, it maintains constant contact between your tires and the road surface. This tire road contact is vital for control, braking and safety, especially in emergency situations or when cornering. Now, let's look at how these damping principles apply in real-world vehicles. There are three main approaches engineers use. First, underdamped or soft damping. This gives you that comfortable ride quality perfect for smoothing out small bumps in the road. But there's a trade-off on rougher surface or during quick maneuvers. But that stiffness comes at a cost. Every bump and imperfection in the road gets transmitted straight to the driver, making for a much harsher ride. That is why most passengers passenger cars use the Goldilocks solution. Critical damping is that perfect middle ground where the suspension returns to equilibrium quickly after a bump without overshooting or oscillating. This project demonstrates how second-order differential equations help us model and tune physical systems like coilover. In summary, critically dampened suspension strike the perfect balance. Most modern cars use near critically dampened setup.
Thank you.